Okay, welcome back. Our next speaker is Yannick Sire from Johns Hopkins University, and he will talk about harmonic max with free boundaries in liquid crystals, like regularity and singularity formulation and applications. That's welcome.
Well, first, I would like to thank the organizers for the invitation. This is very nice to be here. So my talk will be somehow elementary because I would like to give an overview of the latest development, hopefully related to some free boundary problems in geometric analysis and in liquid crystals, mainly liquid crystals. So let me start with some sort of kind of outline. So what I want to, my aim is to investigate boundary value problems with geometric Neumann conditions, both from the point of view of existence and regularity. And the idea, at least for the existence, is to use heat flow techniques. And one of the main novelty developed in the last years has been kind of reformulating part of this problem, some of these problems through integral equations. And thanks to the developments of PD development related to the study of this equation, it could help very greatly to understand those initial problems. And in particular, it helps in understanding something that I will be mostly focusing on is the appearance of blow-up on the boundary. So this is basically a general kind of purpose or outline of the talk. Okay, so let me consider this very classical model problem. So let's take two closed Riemannian manifolds, M and N, and let's isometrically embed the target, and let's consider the Dirichlet energy defined this way, the natural way. And so if you take any smooth enough critical point, it satisfies the following equation. So this is the so-called harmonic map equation. Gamma here is the second fundamental form of the embedding. And this equation, which is a generalization, so the manifold M, the domain has at least dimension 2. And this is, there are other motivations to consider this type of problem, but at least naively, it's a generalization in higher dimension of the geodesic equation. So it's, of course, related to minimal surfaces. And it's been studied by a huge amount of people. So I apologize in advance since I don't quote everyone. And in particular, there are many major contributors in this conference. So a major issue, so basically the study started with a famous paper by Hills and Sampson that I will mention a little bit later, which were considering a heat flow to solve this type of equation. So let me come back to that. But before going into existence theory, how to construct such critical points, or let me take some sort of model which is encoding already a lot of the issues related to this topic, which is whenever the target or the codomain N is the regular sphere, the standard sphere. So then the Euler-Lagrange equation is this very simple looking equation. The problem is that as soon as you look at a weak solution, you figure that the right-hand side is in L1. And from the point of view of regularity, so if you want to do some computation somehow, this is a major issue because, of course, you are borderline for Calderon-Zygmunt. But so if you want to gain regularity for weak solution, you need to exploit all the features of the problem. And one of them is the fact that the right-hand side has a diff-curl structure. And so let me write the argument because actually it takes not a... so one can prove that, so you are considering critical points with solutions of this equation. So of course here, like you get the equation because of this constraint. And so basically this is in L1, but if you use the algebraic structure of the right-hand side, you can prove that actually it's in a better space, which is a Hardy space H1. Okay. So, so actually, like the algebra, I mean, the structure of the equation is so. Of course, this is a difficult lemma. So somehow, like one has to identify what is the structure. So this is not an easy. This is not at all an easy passage to go from L1 to H1. And H1 here is a Hardy space. Okay. So this is let me define it in not a good way, but it's enough for our purpose. This is a space of function in L1 such that the Ritz transform is in L1. And you can prove by using now Calderon-Zygmunt theory that at least in dimension 2, for the domain, if the Laplacian is in H1, U is continuous. And you have gained, and you have gained one step of regularity, and then a classical bootstrap argument gives you that this is smooth. The thing is that, well, okay, there are other ways to deal with regularity of the equation. This is one way. And of course, like the whole point here is to use the difficult lemma and to prove that the algebra or the structure of the equation is giving you this compensated compactness, or this cancellation, allowing you to pass from L1 to H1. There are other ways to do this computation. Kind of this argument was actually found in the late 90s by Hélin. And Hélin proved that if you start from a weak solution from any surface, then the harmonic map equation has a smooth solution. But the thing is that Tristan Rivière proved that there is an harmonic map from the 3-ball to the sphere, which is discontinuous everywhere. So this means that in higher dimension, you cannot hope in general for regularity, but only partial regularity. You're going to be smooth outside of a small set. So one can see just by this. So this slide is summarizing, of course, like years and years of research, and one sees like 2 points in this problem is that regularity is an issue, but existence is an issue as well, because I'm not starting from a Dirichlet problem, right? M is a closed manifold, it has no boundary, okay? So it's really a global issue. Of course, if I'm looking at like a domain with boundary in Rn, I put a nice boundary condition, I can always use some direct method of the calculus of variation to produce a solution, a weak solution. But here, a priori, the geometric problem is whenever like you are like without boundary. Okay, so existence is also an issue. So that's from the mathematical point of view, this problem is pretty interesting because both existence and regularity are issues in themselves. Okay, so let's go to existence. So basically, in the famous paper of Ilse and Sampson at the Hopkins Journal, actually, they design a heat flow so that if you start with a map which is, well, let's say smooth enough between the two manifolds, then you deform it continuously to an harmonic map, to an harmonic one. And so as far as I know, this is the first time that the flow method is used. It's the 50s, huh? So the Ilse and Sampson, the flow method is used to solve like an elliptic equation. I was not like I'm not aware of any before. Well, probably physicists knew how to do that, but at least mathematically. So they proved that whenever the target is negatively curved in a pretty strong sense, they proved that the flow is globally defined. It doesn't blow up in finite time, and it converges at infinity to a solution of the equation. So it's going to be a harmonic map from your initial manifold M into a negatively curved codomain target. So many people after that kind of relaxed a little bit the fact that it had to be like negatively curved in the target. But in any case, whenever you consider the sphere, for instance, for the codomain, for the target n, Struve proved that actually the best you can hope in general is weak solutions which are only partially smooth. So this is a nice, this is a kind of strange feature of the flow, because like, as you remember, like before I said that the harmonic map equation admits by the result of Hélin, Schein-Uhlenbeck, the harmonic map equation, any weak solution of the stationary equation, right, of this map, of this equation, any solution from a surface, a two-dimensional manifold, into a smooth one is smooth. But the flow, actually, what Struve exhibited are weak solutions which are not smooth. So even from a two-dimensional surface. So the flow already is developing finite time singularities. Okay, whereas like the stationary equation doesn't not have. And actually, like the argument of Struve was like epsilon regularity argument, but Chang, Ding, and Ye proved that constructed an initial data so that the heat flow is blowing up in finite time. So the picture is the following, right? So let me draw a space-time, some sort of space-time picture. So this is space, and this is time. So you start with your initial data, right? You run the heat equation. So the target is a sphere. You run the heat equation, okay? You're going to hit the first singular time where you blow up, okay? At finitely many points in space. Then there is a way, because you know exactly how you blow up, there is a way to restart the flow, and then you're gonna blow up again at the time t2 and so on. And what Struve proved is that in any case, you have always a finite number of singular times, which is very important because you want to restart the flow, right? This is like Ricci flow in 3D. You have finitely many. And then the flow is smooth afterwards, okay? At infinity, this is another issue, right? But at least at finite time, you have finitely many singular times. Of course, like, like if you, and this is for general data, if you are assuming small energy for the data, then you can use arguments of Tristan-Rivière who prove that then you can have a smooth flow. So this picture that I described is very vague because one can really quantify, one can have like a very precise way to understand how you blow up. Okay, I will have the occasion to come back to that later. And this is pretty important for the following topics. But in any case, like somehow like the flow already in 2 dimensions has already a lot of features without going in 3 dimensions, right? Okay. So yeah, so I mentioned the first major paper on blow up. By blow up, I mean like it's not a conditional result. It's really constructing a blow up solution by Qing, Ding, and Ye. I will come back to that. And the best result available in the literature now are like an important work of Davilo Del Pino and Zheng Wei, a recent result. So it would be impossible in a finite number of hours to describe all the possible applications of harmonic maps and of harmonic mapping. There are like many, many interesting things you can do with harmonic maps. And this is just like few of, there are many, many things that you can do, both in geometry, in topology, But what I will concentrate in, because I'm a PD person, is like some kind of very interesting models in liquid crystals, and which are related. I will come back to that to some Ginsburg-Landau theory. So let me introduce some these liquid crystal models, which are like some sort of highly non-trivial generalization of this harmonic map flow that I was mentioning. So basically, if you open the physics literature, going back to works of Eriksen, Leslie, Landau, De Gennes, and company, so people in the community were interested in understanding the behavior of crystals. And of course, like as you can imagine, like, because you can see it like in real life somehow. So the liquid crystal should be described both by a macroscopic equation and something taking into account the microscopic behavior somehow of the crystal, which would be typically, for example, the orientation. Okay, so Eriksen and Leslie, so I think Eriksen was in Courant actually, but Eriksen and Leslie developed an extremely complicated model to understand this liquid crystal, and in the late 80s, Franco-Aline kind of provided a simplified version of the model, which is already capturing a lot of features observed in experiments. Well, so if you get a bit acquainted with the equation, I mean, from the PD point of view, it's not really a simple model, but it's for sure a simplified model of the original one. And so basically it couples like two equations. So this one, except this term, is exactly the heat flow harmonic map that I introduced before, and you capture the orientation, and the orientation has to be, of course, on modulus 1, you want the sphere, right? And then the macroscopic equation, the macroscopic behavior, is actually described by Navier-Stokes. If you forget this red term, this is exactly Navier-Stokes equation. Okay? So there is a model in dimension 2, and there is a model in dimension 3. I will mention a little bit about that. But this model couples like these two equations, right? And actually, once again, even if it's a simplified model of the original physical model, this is pretty much relevant to explain a lot of the experiment. Because of course, like one of the things which are like an important part of the work of the thesis is the understanding the appearance of defects. Okay. And do you have filaments? Do you have only point defects? Do you have something higher dimensional than filament? And this time, it happened that this equation captured pretty well. This system captured pretty well this behavior. So yeah, it covers these two equations. And one of the great features of this model is that the coupling is somehow, once you have like some a priori regularity on you, right? Let's say, for instance, it's really like just a forcing term, right? Or Navier-Stokes, right? So from this point of view, it has a very good structure, right? Okay. So as you can imagine, so here you have more, so here I put like some references about Navier-Stokes, which would be, of course, it's also, I apologize in advance. There is not enough. Basically, it started with Le Ray, and then, and here more references about the harmonic map flow. And of course, as you know, there is a dichotomy. I mean, there is a strong difference between dimension 2 and dimension 3. Well, here, this is even worse somehow because, I mean, roughly speaking, Navier-Stokes does not blow up in dimension 2, but the harmonic map flow blows up, right? So here, already in dimension 2, you blow up, right? Somehow. So this system is already pretty complicated in dimension 2. So as far as the liquid crystal flow is concerned, so the partial regularity, because of course, like you have a partial regularity that I was mentioning for the heat flow of harmonic maps, but you have also a partial regularity you can develop for Navier-Stokes, so-called Caffarelli-Kohn-Nierenberg. And in dimension 2, Lin and Liu and Lin and Wang develop like the partial regularity. And in dimension 3, the situation is much harder. And actually, there is no the equivalent in dimension 3 for this model of Caffarelli-Kohn-Nierenberg criterion. This is the problem in dimension 3 is very hard. Let me explain a little bit on this assumption. As I was mentioning before, the heat flow in general of harmonic maps is blowing up in finite time and finitely many time, at finitely many like singular times. The thing is that if you put a restriction on the image of the domain by the map, so typically here you put that, sorry, this D naught should be a U naught. That the initial data for the heat flow of the harmonic map, right, the orientation of the crystal is in the hemisphere. Then you become, so it's been known for a long time for the stationary equation, but you can do it also for the flow. You become subcritical, and you don't develop finite time singularities. So you see, like this assumption in dimension 3 prevents 2F blow up at like waving hand, prevents 2F blow up for the heat flow part, right? For the harmonic map flow part. However, remains Navier-Stokes in 3D. But still, Lin and Wang were not able to prove a full Caffarelli-Kohn-Nierenberg, even if the harmonic flow part of the system is not blowing up. It's a very hard, very interesting problem, very hard, like mathematically. And very recently, Lai Lin, I will come back to that, Lai Lin, Wei, Wang, and Zhu like proved like finite time blow up in 2 dimensions at finitely many points, and I will come back to that. Okay, so up to now, I was only describing, so let me come back to the initial one. I was only describing somehow, or like the upshot was like the domain has no boundary. So now let's put a boundary on the domain and let's look at what is the natural boundary conditions that you want to put, and what are the problems like you want to look at. So as far as the harmonic map system is concerned, somehow so of course if you put if the domain has a boundary, you could always put Dirichlet, right? But geometrically, this is not necessarily what you want. And so what you want is to leave the boundary free somehow, okay? And if you want to leave the boundary free, this means that you don't prescribe Dirichlet data, right? You would just prescribe a constraint, okay? So you just say, so the picture is the following. So you have your map. So now M is as boundary, okay? And you would look at a map from M into N, right? And you put on top of it, you put a constraint that the map maps the boundary of your domain into a submanifold of N. Right? These are dimension K, these are, okay, and these are dimension whatever, N. Okay, and K is less than N minus 1. So from the point of view of, if you think about harmonic maps like a kind of a class capturing homotopy of the domain, from the point of view of relative homotopy, this problem has really a sense, because, but now the geometric situation is more complicated because you have 3 manifolds to take into account, right? You have the domain, the codomain of the map, and a submanifold which is on which you constrain your boundary, right? So these harmonic maps, okay, when you look at the critical point of that, right? These harmonic, assuming everything is smooth for the moment, these harmonic maps are called harmonic map with free boundary. Well, it's not a free boundary in the way of a classical way of free boundary. I'm not trying to solve a problem where the domain on which I set my equation is unknown. Huh? So it's not a free boundary like in the Caffarelli sense. However, geometrically, this is the way the problem is formulated, and at the level of the PDE, so this is what I meant earlier during the first slide, the geometric boundary Neumann condition. So this is inside, right? Inside the domain, the harmonic map equation, right? You have your constraint, right? And, well, when you write the first variation, I mean, you have like the geometric Neumann constraint, which is the fact that, right? Okay, so this is more of a constraint problem than a free boundary problem from the PD point of view, okay? So, as you can imagine, all the problems that I was mentioning before, existence and regularity remain, but here on top of it, you have to understand boundary irregularity, okay? And so, coming from PDEs, studying boundary irregularity, there are many ways to do that. But here, particularly using reflection argument, but here, you don't want to lose the fact that you have an information, you are like orthogonal to the tangent space of the submanifold, sigma q, right? So you could reflect to understand, because by reflection, of course, the boundary regularity becomes an interior regularity, but this is not necessarily the best way to look at the problem. Okay, so this is what I want to convince you about in the next slides. As you can imagine, once again, you can build a flow. Actually, it's been considered by Hamilton, Struve, Chen, and Lin, right? And so if you look at what it is, right, this is a heat flow of the H1 energy, right? So you solve the heat equation inside, you preserve the constraint, and you move, right, at every time the boundary. All of this is I mean, there is like a natural analog of the previous theory. So next, tomorrow, they're going to talk about that, I guess. So there is there are good reasons to look at harmonic map with free boundary. And one of them is the fact that they are ubiquitous in the extremal metrics for the Steklov problem. So it's been looked at by Daniel here, Frasian chain, Laurent Petride, and what I would like to discuss. So I have no time also and to develop the geometric interest of looking at this and understanding the regularity, looking at the existence of such maps and their regularity. But let me mention that what I would like to emphasize is this new point of view using half harmonic map, which were introduced by Francesca Dalio and Tristan Rivière. And so basically, which offer a new point of view and which allow, like, and I will come back to that because in the case of the flow, which allowed us to prove like blow-up result. So, so there are good reasons, like, to look at harmonic map with free boundary besides their PD interest, I should say. So basically, coming back to the flow, so this flow that I just mentioned here. If you remember what's happening in the case without boundary, Struve developed like a partial regularity result, right? And Chang, Ding, and Ye proved like blow-up, okay? So Chen and Lin, looking at this flow, ask the following question. Well, let's take the domain being smooth, okay? And the target being like, for example, a Rn or like flat torus, if you want. And sigma, a smooth compact manifold. Is it possible to cook up a smooth data so that the flow is blowing up in finite time? Okay, so the harmonic map flow with free boundary has no global solution. Well, so exactly, the question of Chen and Lin is an analog of the blow-up result of Chang, Ding, and Ye, but for the harmonic map flow with free boundary. Well, the thing is that this problem of harmonic map with free boundary is really a global, non-local problem. So in particular, when you try, so basically there are not like infinitely many ways to construct blow up. One of them is constructing barriers, right? Okay. So if you have a barrier from above and from below, right, which is blowing up at the correct rate, then you stuck your solution by whatever argument you want, and then it will give you automatically by Perron or method something which is blowing up in between. Well, the problem is that this type of argument, first, is a very scalar argument, okay? And in the case of Chang-Ding and Ye, this is done through some reductions which are impossible to do in the harmonic map flow with free boundary. And let me show you why it's very hard to do. So let's take the simplest possible situation somehow, which is this M here is a half plane, right? And my target is S1, right? For sigma, sorry, and then N is R2, okay? So then the geometric boundary condition that I was mentioning is just this one, right? So this is a very simple equation, right? You are solving the heat equation inside, right? You are like constrained to the circle, and well, you have this. This is where the nonlinearity is coming, right? So actually, I might be able to come back to that. It depends. So what you can construct weak solutions of this flow, which are partially smooth, right? And this is done in a classical way by taking Gisborne-Landau relaxation. So Struve provided one possible relaxation, and with either Segati and Shangyu Wang, we looked at another type, which is a singular perturbation on the boundary. But in any case, let me exhibit for you the fact that this problem is non-local. So let's take a stationary solution of my equation, okay? So this is this problem. So you have an harmonic function in the half plane, which is constrained to the S1 in the line, right? The boundary of the half plane. Well, if you denote V to be the trace of your harmonic function in the half plane, then you can prove that the root of the Laplacian of V is this condition is equivalent to square root of the Laplacian of V orthogonal to the tangent, okay? When you write down what that means, you get this equation for V, and this is Daillot-Rivière map. Okay? So there is a correspondence, okay, at least in Vivre, this very special and simple geometric situation between what happened on the boundary, which is Daillot-Rivière map, so a critical point of the H1 half energy. Remember that here you have the root of the Laplacian. Okay, and its harmonic extension, which is an harmonic map with free boundary. So whatever you want to do, you can jump from one representation to the other. So in the first paper, they introduced those maps. Francesca Daillot and Tristan Rivière proved that they are C alpha, and actually it's smooth. And then with Vincent Millot, we kind of investigated some Gisborne-Landau, some construction of such maps, and Junchen mentioned them yesterday that you can cook up flows. I will come back to that, and there have been several works related to this half harmonic map. But what I would like to emphasize is that of this correspondence, right? Because it's very useful to understand some problems which are global in nature, like Steklov type problems. So one thing that is also interesting is that those maps, if you take this, the half, so let me call these maps half harmonic maps, half because of the half here. There are good reasons why it's R here and half here, because it is a critical equation, and this one half and one here plays a role of 1 and 2, and 2 for the dimension for the classical harmonic one. This means that this, you remember L1 result, right? From R2 into S2 into any manifold, you are smooth for harmonic maps. Here it happens for S1 into any target, right? So this is like, you are critical in dimension 1, if you want, okay? And there are good reasons for that. But in any case, you can cook up, of course, a flow which is associated to a harmonic map, which is a gradient flow of H1/2 energy. Okay, well, it happens that this flow is a bad flow. Because it has no monotonicity, I will come back to that later if possible. So basically, like in a more general way, this computation can be done for other geometries. So in general, let's take in general the harmonic extension. Let's take a manifold omega with boundary M, and let's take the directly to Neumann map, okay, for the harmonic extension of the boundary data, right? So you take, you have omega, right? Omega. You have M, which is a boundary of omega. You take a map F on the boundary M, you extend it harmonically, and then you take the directly to Neumann map. Okay? So then if you open one of the Taylor's book, right, you can prove that the directly to Neumann map, okay, is always the root of the Laplacian, the Laplace-Beltrami on the boundary, plus a zero-order term, but which is a pseudo-differential operator of order 0. And this is not a multiplicative operator, by the way. Okay? So this point of view is some sort of generalization of what I was mentioning before, where you could do actually all the computation. But what it tells you, at least at the level of regularity, and which is important for me, is that the main order is the square root of the Laplacian, right? Of course, like as you can imagine, this type of computation is only working in the smooth setting. Huh? Okay, if you are like non-smooth, well, if you're not too non-smooth, too singular, you can still have a replacement. But if M is like a pretty strong singular space, well, it's much harder. Okay, so let's come back to so once again. And I hope it's going to be clear later. Like now we have a choice, right? Whatever we are looking with these geometric boundary conditions, right? Either we look at a problem inside and a Neumann boundary condition, or we manage one way or another to reduce everything up to additional error term, which hopefully are lowered to something on the boundary. Okay, but now we have equations which are non-classical somehow. Okay, in the sense that they are integral equations. But I mean, recently, well, now it's not that recent, but in the last 25 years, there have been like many works devoted to understanding this type of object. So let's go back to the question of Lin and Chen and Lin, okay, about the blow up for my flow. So let me write again the equations. So I am caloric inside, right? I am caloric inside. Okay, here this is R2 plus. Huh? I'm caloric inside. I have this geometric Neumann condition. And I have the constraint, right, which is the fact that U of the boundary of the half plane, which is, of course, R, is in S. Right? Well, so a few years ago, with Junchen Wei and Yuqian Zheng, we provided a positive answer to this to the question of Chen and Lin. So the statement of the blow-up result is a bit complicated. Let me just like simply explain the thing. So basically, pick any point, right, on the bound. Well, okay, first let me do like the trivial comment that inside you are caloric, so nothing happens as far as blow-up is concerned, of course. Okay, so the blow-up has to be on the boundary. Okay, so pick k points, well, and whatever k is, on the boundary, finite on the boundary, then you can cook up an initial data such that the flow is blowing up by geometric bubbling, so by rescaling, okay, in space and time, lambda I is the rate of entire solution of the stationary equation, right? In this way, okay, exactly what Junchen introduced yesterday with some sort of Struve global decomposition. Okay, I don't want to write exactly what is omega, but think about an entire solution, okay, right, extended to the half, harmonically to the half plane, right, which plays a role of a bubble, okay, so an entire harmonic map from S1 into S1. An entire harmonic map from R to S1 into finite energy, extended harmonically. So this is really like looking like this. You pick K points and you blow up like this, right? At your K points, right? So the rate is type 2 and, oops, sorry. And basically, the concentration, of course, is at the level of the gradient, right? Because it preserves length 1. So in this type of business, of course, there is, like, you want to understand where the blow-up is occurring. And here, like, it's going to be important for later. Like here, it cannot happen inside, right? Inside the domain. You are like caloric inside. It happens on the boundary. Well, if you keep in mind what I said about the stationary equation and the fact that it was actually a non-local problem, well, this problem is also non-local. And you can prove that somehow, okay, in a precise sense, it's equivalent to solving this equation on the boundary, right? So forget this kind of kernel, okay? What is this term? So this equation is exactly the parabolic analog of this one, right? Well, no, yeah, on this one. If you replace minus Laplacian by the heat operator. But the thing is that this is not a classical space-time symbol, right? Classical space-time symbol would be if there is like a separation between time and space, right? Here, like if you go Fourier Laplace, this is this kind of weird symbol, right? And then you can even derive like a Poisson formula, right? But somehow, my whole point here is that the equation that you will be crucial for our construction of the blow-up is the fact that somehow the problem reduces to that. And this is something which is closer to what people looked at before. Okay, except that, of course, you have to deal with all these non-local terms. This means that in particular, well, sub and super solutions are not working very, I mean, you have to use all the argument. But this is because, so this is because we could understand after all the work that the problem reduces to blow up of that we could actually prove answer positively or provide a non-trivial answer to the question of channeling. So this type of thing, if you keep, like if you have liquid crystals in mind, this type of thing motivates the following question. Well, if I go back to this liquid crystal problem that I introduced, that I mentioned before, can we cook up some natural boundary conditions so that, like, actually you have a model with Neumann boundary conditions for liquid crystals? Okay, because by many means in physics, this is also the physical boundary conditions are Neumann conditions. Well, it happens that the answer is yes. So with Frank Hualin, Junshan Wei, Yifu Zhou, we looked at the following model. Let's take the same equation, but now you design free boundary conditions for your domain. So in the previous model, the original model of Lin, they looked at Dirichlet boundary conditions. And now, we consider this Neumann boundary condition. So here you can notice that for the heat flow of harmonic maps, you have like this geometric Neumann problem, this constraint equation. But then what are the natural, and I will say why it's natural, boundary condition you have to put on the velocity? Well, this is this. So you have the stress tensor, okay? And these are these Navier slip boundary conditions, okay? So when you look at, when you try to derive like a PDE having like physically meaningful, you want to prove that at some point it dissipates energy, right? So, of course, like you have another formulation that you could consider for the boundary value of the boundary case. It would be like more closer to this situation, okay? But you can show very easily that there is no energy dissipation if you take this geometry. So you really need to have like a target for n, right? And like the constraint to be like in the target, you know? Once again, I mean, when you have this harmonic map with free boundary, you have three manifolds, right? The domain, the codomain, and the manifold constraining the map, right? If I take the codomain to be Euclidean and S1, it's not, the system you derive is not, doesn't dissipate energy. But if I take the codomain to be the sphere and sigma to be a curve, okay, on the sphere, right, then actually it does dissipate energy, and even better, the Navier boundary condition appear naturally, okay? So actually, like, if you look at the equation, as you can imagine, like, once you have the equation, you just like do the classical energy estimate or energy computation, formal energy computation, and actually you figure that, let me skip that, using the equation and the boundary condition, actually everything is consistent, and you have a basic energy law, okay, which is like, you see, the variation in time of this energy is negative, non-positive, right? Okay, well, so let me skip that. The equation in particular has an additional symmetry, which is useful to derive the result that I will mention very quickly, which is like, because of the way it's designed, like, it has some nice symmetries. And, but let me skip that. So let me come to the thing that we proved with Francois, Yifu, and Junchen, and Shapir last year. Is it like, we proved like some finite time blow up for this liquid crystal flow with free boundary. So as you can see, the statement is very similar to the one that I gave for the heat flow of harmonic map with free boundaries. W1 and W2 are also bubbles, okay? So, but let me mention that, so the rates are what they expect. This is the harmonic map heat flow part, which is blowing up. And here, like, the statement and the construction are more complicated because of interaction between inside and out and the boundary. So one of the points of these models and all the things that we've been developing in the last years is trying to understand, indeed, as I was mentioning, like the boundary regularity or boundary blow up. And here in this type of model, right, what you get is that if you look at the original, I mean, the paper of a couple of years ago of Chen-Chi Lai, Francois Lin, Chengyu Wang, Juchen Wei, and Yifu Zhou, they constructed for the liquid crystal like interior blow-up. But here you have a boundary behavior which is non-trivial, so you have also boundary blow-up, right? Okay, you have this mixture like that. Well, the point is that so let me skip that. The point is that you choose a priori in the construction, you choose at the beginning where you want your blow points, right? If you want them inside, it's a construction of Lai, Lin, Wang, Wei and Zhou. If you take them only on the boundary, this is somehow much more related to the construction and to the statement for the harmonic map heat flow that I was mentioning, right? Well, the hard part, or the more interesting part, is that when you take points where you want to blow up both on the boundary and inside, then you have this sort of interaction that you have to take into account, okay? And this makes the thing, that's why it makes the thing interesting. So this model, so I proved with Yifu and one of my graduate students, Yantao Wu, that the elliptic software with free boundary in 2 dimensions admits indeed global solutions which are partially smooth. The global weak solution in 3 dimensions is completely open for many, many reasons, which are because many things are not available completely in the free boundary case, even at the level of the harmonic map. And let me mention, related to this boundary blow up and this interior blow up, that, okay, so you can prove, because this is something I alluded before, that when the heat flow of harmonic map is blowing up, you know how it is blow up. You extract the bubble and you have like finitely many, and you have exactly the energy of the bubble, right? Which is quantized by A pi. Here, like the boundary blow-up is a half harmonic map in the sense of Dalio and Rivière, or like a harmonic map with free boundary, right? Which carries half of the energy of interior bubbles, right? So the half bubbles has energy 4 pi, right? So as I was mentioning, that there is bubbles in the interior, okay, bubbles on the boundary, and the 2 situations, okay? So basically, like the whole problem of this, the whole construction, is based on understanding these interactions. And let me advertise very briefly what is a technique used to do this blow-up results, which is something which has been developed by Cortázar, Del Pino, and Musso, and Davila, Del Pino, and Wei, and all the collaborators, is the so-called inner outer gluing parabolic method. So parabolic version. So basically, it's a parabolic version of the gluing, of the geometric gluing that has been done for several years and very much refined in the elliptic case, except that in a parabolic setting. So it's pretty technical, but the idea or the strategy is very similar from follow the strategy that you would do in the stationary case, is that you try to construct first a good approximation, which would be like rescalings and of these bubbles that I was mentioning, right? Then you kind of split the perturbation in 2 terms, right? One which is concentrated close to the spike and the outer problem, and you derive a system for both the inner and the outer. And why is it really a parabolic thing? And it doesn't apply, at least like as far as I know, as it is today for wave maps or Schrodinger maps or things like that, is that you use the fact that parabolic theory is improving regularity and in particular improving decay. So if you have a right-hand side which has decay whatever, like for the parabolic equation, the solution will have better decay, right? And this point is L infinity bounds that Johnson mentioned yesterday very often are crucial to be able to run the gluing construction. It's not clear at all, at least to me, how to develop like a theory which takes into account all the geometric problem, but of wave types. So maybe I should stop here. Thank you very much for your attention.
Many thanks for Professor Sire's wonderful talk. Any comments or questions?
It is like
You have uniqueness. in the class of this is exactly in the parabolic analog, the free boundary analog of the original paper of Wang and Lin. Yeah. And by the way, like I mentioned, like there is a very interesting problem that I would like to advertise, that if you take the original liquid crystal flow of derived by Lin, and you open the paper where they do the Caffarelli-Nirenberg 2D partial regularity, they don't prove that when you blow up at a time t, you blow up at finitely many points. They don't prove it. They prove that you blow up at most at a countable number of points. If you have in mind what happens for the heat flow of harmonic maps, Struve tells you, no, you blow up at finitely many. The thing is that this system is so complicated that they don't have enough energy control, and even actually the problem is the pressure as usual, that they are able to prove that they blow up at finitely many points. And it's an open problem. They conjecture that it should blow up at finitely many points, but we don't know how to prove it. For this flow, for the free boundary, this is the same. So I don't know any way, actually, because the estimates are too bad on the pressure in particular for Navier-Stokes part. Even in 2 dimensions, the estimates are too bad to be able to run the concentration argument to prove finitely many points. And so, yeah. But otherwise, like as usual, like the uniqueness is an issue, and well, you have unique only in special classes.
Okay. More questions? If there is no more questions, let's thank the speaker again.
That's it.